Hi all, welcome to yet another blog in the EKS Anywhere saga series. And this time around, we are going to be focusing on a very interesting trend in the marketplace where customers all alike want to deploy Kubernetes directly on the bare metal nodes actually. So this blog is going to be focused on how do we deploy EKS Anywhere on bare metal nodes, as opposed to my previous blogs where we had shown EKS Anywhere deployments and use cases on a virtualized stack. Note that EKS Anywhere supports Ubuntu, Red Hat, and Bottle Rocket alike on bare metal configurations. But before we delve into the specifics here, let me introduce Raj. Hi, Raj.
Hi, everyone.
Raj is my colleague, and he is well positioned for all the cloud native landscape and application modernization. He is placed in the Dell Consulting Services. Raj, anything you would like to add?
No, you've explained it very well. Have a background in Pivotal Cloud Foundry and lately Kubernetes and anything to do with cloud native, as Amber mentioned.
Thank you. So why this blog? That's the most important reason, right? As we find ourselves in the midst of deploying EKS Anywhere on bare metal, we often look upon the official documentation page, and my experiences along with some of the other colleagues is there are certain challenges to actually interpreting that documentation, and customers of ours and my colleagues have got kind of they've got challenges at every step as they start deploying these clusters at scale. Hopefully in this blog, I think we will be able to comprehend comprehensively what it takes to deploy these bare metal clusters, and we are really going to actually dwell under the hood of how this whole interaction and workflow occurs when the bare metal clusters get created. I think we'll spend a little bit of time first understanding the nuances and the basic elements of EKS Anywhere on bare metal. Let me share my screen if that's okay. Okay, I've got a few slides that take this discussion into the detailing part, but let me start by explaining you this particular slide. What you see here on my screen is a typical workflow that one would expect when you start deliberating or delivering EKS Anywhere on bare metal. So you have, like any other installation of EKS Anywhere, an admin node and the worker nodes, which will comprise of the control plane and also the worker nodes in a particular cluster. So let's assume that the orange column here is the cluster nodes, and this particular blue column is the admin node. Now, first question, which OS distribution would I like to deploy on EKS Anywhere for bare metal? Like I said, it supports both, or actually all the three: Ubuntu, Red Hat, and Bottle Rocket. Now, the first and foremost question is, does my admin node be, or should it be a Ubuntu node for a Ubuntu based cluster? Or should it be a Red Hat node for a Red Hat based cluster and alike? So the answer is no. You can use a Ubuntu admin node equally well to create a Red Hat based cluster. Or you could use a Red Hat node to create a Ubuntu based cluster. So these two are independent in that nature. What is most important is that whichever target cluster, whether a Ubuntu or a Red Hat cluster that you want to build, the OS images for those nodes are pre-created using the image builder utility that is supplied by AWS. In my previous two blogs, I have detailed the exact workflow of how to create a Ubuntu based OS image for the EKS Anywhere nodes for the bare metal operations. And also I've detailed a blog with a video for the Red Hat OS creation. So those two blogs should help you in creating the OS images. Now, once these OS images are created, they need to be kept somewhere which could be accessible through a web service. So typically, we double up our admin server also as a web server, or sometimes it's best to actually have a separate web server, which could be serving those images as they will be getting downloaded during the workflow on these nodes. So now let's start with the most important fact of EKS Anywhere. We all know that uses Cluster API under the hood to interact with different infrastructure providers. And when I say infrastructure providers, Cluster API supports, I think, about 50 plus different infrastructure providers, including vSphere, Apache Cloud Stack, Nutanix, and many other, including the public cloud providers, right? For bare metal, for Cluster API, the infrastructure provider is an open source project called as Tinkerbell. Now, it's necessarily not an infrastructure provider, as in it's more of an infrastructure, provisioning tool as such and lifecycle management. But let's qualitatively put that as an infrastructure provider for bare metal, because that's going to be the interface. So if you see the sequence, it's EKS Anywhere talking to Cluster API, and Cluster API having its extensions for Tinkerbell, and whatever actions that we invoke, cluster creation, cluster expansion, and all those things, upgrades, they're ultimately going to be called through Cluster API, and those calls are going to be placed on Tinkerbell. And Tinkerbell then speaks to the individual nodes which form the part of the cluster. Now, this particular slide, the pictorial, is about exactly how Tinkerbell communicates with those cluster nodes right from the get-go of the cluster invocation. So let's say when we create or hit the create action by saying EKSCTL create cluster, the action is invoked by Tinkerbell, okay, and it communicates with the worker nodes or the cluster nodes. And how does it communicate, basically? So as a prerequisite, your servers, which are actually a part of this bare metal cluster, need to have some out-of-band BMC connection. Okay, that's very important. In this particular video, we are going to be showcasing Dell servers, Dell R760, which have iDRAC as the representation for the BMC controller there. Okay, so we have iDRAC, which is the out-of-band communication channel. Now we need to supply Tinkerbell with the iDRAC communication information, including the credentials and whatnot. But as a result of that, Tinkerbell basically communicates with the iDRAC on the respective node. So let's say if you're building a 3-node cluster, it would go sequentially and talk to each of the iDRACs, invoking certain things. Now, what are those certain things? It starts with basically the whole operation or the sequence starts with PXE boot, okay, which is a network boot option. Now you can see that for that to occur on your worker nodes, you need to have the UEFI boot option selected, and the NIC that is going to participate in the cluster communication needs to be enabled as a PXE device, actually, right? So basically it will set the PXE boot options on the worker node or the cluster node, and then do a power recycling and things like that. And that's what starts the PXE boot process. Now, as a part of the PXE boot process, okay, the first step, now you can ignore this without BMC. If you don't have a BMC, then what do we do? But let's focus on this. So once the PXE boot process starts, we can see that there is a DHCP request that is actually sent out from the NIC that is intended to participate in the PXE boot. And that NIC has a particular destination or a MAC address, right? Now that DHCP request should hit the Tinkerbell. Now Tinkerbell runs on the admin server initially as a bootstrap kind cluster, as a application or a container inside of that bootstrap kind cluster. Inside of the Tinkerbell stack, you have SME, Boots, and other services in which one of the element or the functionality is to serve a DHCP, service basically, right? So it's listening for all incoming DHCP requests. Note that at this stage, it's vital and important to highlight that on this particular layer 2 network, in which you have the admin node and the cluster nodes, there should not be any other DHCP server sitting, else it can create conflict of sorts. Okay, so let's assume that there is no DHCP, external DHCP running in this particular layer 2 segment. So the DHCP request that comes in from this particular cluster node, which is trying to pixie boot, eventually gets responded by the Tinkerbell service. Now, when we create the cluster, there is a file that we need to supply, which is called as hardware.csv, and we'll walk through that file and the contents and whatnot. But in that hardware.csv, there is a line-by-line mention of every node with certain fields of information. So for every node, you have one line item that specifies the node specifics there. And in that node specific, you have the MAC address and the IP address that has to be assigned to that. It's like a reservation of sorts, right? So when the DHCP request comes in, Tinkerbell notices that it's coming from a particular MAC, and hence it has to be awarded this particular IP address. Okay, so that's how you basically sequence out the IP assignment. Once the IP gets assigned, you also have the pixie boot or the DHCP options being set so that it will also download a auto pixie file, which is like an instruction set. Now, as a part of that process, what happens is basically a minimal utility called as hook OS, okay, which is a minimal OS, which has the further instructions to download the OS images and do other custom actions and all that of preparing the node. All that needs to be or will be executed as a sequence of workflows. But it all starts with the node sending a pixie boot request, the DHCP request response happening. As a part of the response, a file called as auto.pixie gets downloaded onto the cluster node, and then what follows is the download of the hook OS. Once the hook OS is basically installed, hook OS then will start the minimal configuration, and then it will start downloading the actual OS image from the location mentioned. And finally, what results is the cluster node, that specific node is fully installed. The EKS Anywhere will say that this particular node is ready, and it will move on to the next node, and then the next node, and then the next node. Once all the nodes are ready, this is important, the Tinkerbell components which run on the kind bootstrap cluster, this kind bootstrap cluster is temporary, like the virtualization stack also. This is a temporary bootstrap cluster. But eventually, this Tinkerbell stack is moved from the kind bootstrap cluster onto the actual target cluster, on which it lives as a set of Kubernetes services, basically. So your Tinkerbell gets exposed through a as a load balanced service and with a API or with an IP address and all that actually. So the entire Tinkerbell stack moves here in to the actual target cluster. The kind bootstrap cluster is deleted, and unless you re-invoke some other command like an upgrade or a scale out and scale in, wherein now all lifecycle operations are directly performed through the Tinkerbell stack living on the cluster, as opposed to re-invoking a kind cluster with Tinkerbell components. So that doesn't happen, because now the Tinkerbell has moved out of the kind bootstrap cluster, living on the actual cluster. Now, why am I explaining to you in such details is because you will see references in the cluster configuration file of providing a Tinkerbell IP. Now that Tinkerbell IP is the IP address that will be assigned to the Kubernetes service that is exposing the Tinkerbell functionality. Okay, that's one. Second most important thing, you can see that because there is a DHCP process involved here along with the Pixie boot, your admin node and your cluster nodes, they are supposed to be in the same layer 2 broadcast domain, same VLAN. There should not be any L3 between them as such. Okay, this is important. A lot of people don't realize this, and sometimes they place the admin node in a separate VLAN and the worker nodes in another VLAN, hoping to actually see some kind of cluster creation, but it will fail because there is the whole Pixie boot process and the DHCP process will not yield outcomes there. Okay, so this is just a generalization. Obviously, there's a lot of devil in the details as such, and we will walk you through that particular context. But hope this kind of places an initial understanding. Raj, do you want to add anything to that point actually?
No, you've explained it very well.
Okay, thanks. Now, like I said, we will be doing a demonstration of sorts, and we will try to actually, do this particular demonstration for both Ubuntu and Red Hat based images. So let's see where do we go from here actually. To start with, let's highlight and showcase what do we have as an inventory so that you can understand, the makeup of our cluster actually. So I'll ask Raj to share his screen and we will walk through some of the iDRAC information on all the 3 nodes to start with actually. Okay, yeah, let's start with this itself. I think this is also interesting, hardware.csv. So this is the hardware.csv, which is fed as an argument to the EKS Anywhere create utility, right? The EKS CLI. Like I said, you can see that there is a single line entry for each node, and there are columns of information starting with the host name, the BMC IP, the BMC username, the BMC password, the MAC address, the IP address for reservations, along with other things like netmask, gateway, name servers. And the last one being, this is also important, what is the type of node? So is it going to be a control plane or is it going to be a worker node? And the device on which the whole, the thing will be persisted, right? So this is also important. And in our case, we have a SATA based device for your control plane. And, for our workers, we have the NVMe drives actually, right? Now, very important, the iDRAC network should be reachable also from the admin node actually. So there should be some form of L3 connectivity from the admin node to communicate with the iDRAC IP addresses. So all these servers, you can see they belong to 197, 172, 29, 197. So that's the iDRAC IP addresses for out-of-band communication. And for your actual NICs, which will be participating in the cluster, it's 172.29.198.xyz, whatever it is, right? So I hope this is the first step is clear. Preparation of the hardware.csv, depending upon how many nodes you have, you got to populate this particular information correctly. Now let's move on to the iDRAC consoles. So you can see this is the first node there. 197.60 is the iDRAC IP address for your control plane intended node actually. Okay, and what's very important is that let's look at the NIC information here. So in our case, we do have a bunch of network cards that we play along with for various demonstrations. In this case, you can see there are 3 network cards. Our intended card for the communication of the cluster or the cluster nodes is NIC slot 3. That's a Broadcom card. One thing that's a caveat of sorts and important and imperative to understand is that the hook OS utility, which then boots the cluster with the actual OS images, has limited compatibility for different kind of NIC vendors. In our case, when we experimented with some of the Intel NICs and all that, we found certain challenges of compatibility, from a default hook OS perspective. So either you, go ahead with a compatible card, or there is a set of procedures that you can perform to create a custom hook OS. So you download the default hook OS, the latest releases, and then there are some steps to be run to actually create a custom hook OS which has the firmware and driver support for your particular NIC of choice and all that actually. But in our case, what we've just done is we've just kind of standardized on the Broadcom card here. So here in NIC slot 3, we do have this Broadcom, and if you click on that, we will see the MAC address actually is 4690 is there as a part of the hardware.csv there. So maybe we can flash out the hardware.csv. We can correlate that information as well.
Right.
Yeah, 46.90, right? And likewise, we do have the iDRAC for all the others, but we won't go there. It's the same. Now, other thing that is very important is if we click on the configuration and boot settings, BIOS settings, setting the BIOS correctly is a very important and crucial step here. So you can see that the boot mode that has to be observed has to be set as UEFI. Okay. Now for both Red Hat 9.x and Ubuntu, we need the value to be set as UEFI, and the UEFI boot sequence should include the PXE device or targeted PXE device. So if we scroll down to the network settings, so you need to have the number of PXE devices set accordingly. In our case, we are using the PXE device 1 settings, okay, and that PXE device 1 is enabled, and what corresponds to PXE device 1 is the interface, which is NIC in slot 3, port 1, partition 1, which is the same Broadcom NIC that you saw. We have just one port active on that, so we are mentioning that as the the PXE device 1 here, and that is enabled, and that is also a part of the UEFI boot sequence actually. So this is important. The other most important thing is sometimes you are not deploying a production cluster, you're doing it for fun, like what we are doing. If you have at any point of time deployed a cluster on a particular node and you want to redeploy the cluster on the same node, right? You need to make sure that every time you do a fresh install of a cluster, your storage disk, the virtual disk which is associated with your storage, is deleted and recreated. Okay, this is very important. Otherwise, what we have experienced are leftovers in terms of PXE boot configurations and IP addresses and all. It creates a conflict where your nodes may not boot correctly. So the best practice there is, whenever you start a fresh deploy of a cluster, make sure that your entire disk is recreated, the virtual disk. Okay, so those are two important things: the UEFI boot settings, the PXE settings, device settings, and then the virtual disk cleanup and recreation. Other than that, everything else is flat out. There's nothing. It's just a fresh server in that case actually, right? Likewise, if we can just toggle around the three, so let's see the other iDRACs. So this is .60, this is .67, which is the worker node, intended node for worker 1, and the next one is .68, which is the intended node for worker 2. Note that we are communicating via the 197 subnet, which is the iDRAC there actually, right? Our intended subnet for the NIC as such, which was the cluster NIC, is 198. Okay. Now we will talk a little bit about the cluster configuration file, which is equally important. Now, anytime that you run a cluster create command, you have to pass the hardware.csv. Along with that, you have to put forth a cluster configuration file. Now, first we will scroll down and start with line 46 there. 46, yeah. So you see that we start with line 36, and then I'll come to the top lines. But line 36 suggests what is the Tinkerbell data center config. Now, like I said, like vSphere or any other infrastructure provider, Tinkerbell is assumed to be the infrastructure provider for Cluster API and EKS Anywhere for bare metal. So we have to provide certain inputs to the resource, which is of the kind Tinkerbell data center config, specifically the OS image URL. Now, this OS image URL is the location from where, as the nodes boot up through Hook OS, the OS image will be downloaded into those specific nodes, right? Which will be the cluster nodes. Now, as I said, it's upon you. You can place this particular image. Now, in this case, you are looking at a Red Hat image. It could be a Ubuntu image. But whatever that OS distribution is, you have to service it through a web server. And in case you are using your admin server to double up as a web server for OS image URL, make sure that the web server that you are running does not run on port 80. The reason being, the Tinkerbell service in the Bootstrap cluster, when it gets invoked and created, also starts a web service which runs on port 80. So in our case, we are using a web server which is a different node other than the admin node. So it's 198.74 and our admin node is .72. Okay, so 172.29.198.74 is a web server. Inside of that, we have the web directory we have created or positioned our image there. So we have to specify this URL. Second, the Tinkerbell IP. Now we know that when the Bootstrap cluster gets created, the Tinkerbell, which is resident and doing the initial workflows, is a temporary one. Once it moves out of the kind cluster to the actual cluster, where it will live for all lifecycle management of the cluster itself, needs to be exposed as a service, load balanced service, and hence it needs an IP address. So we need one IP address which is excluded from, or is not reserved anywhere else. It's non-conflicting and all that. And this will come up as an IP inside of your target Kubernetes cluster and living and breathing as a Kubernetes service for the Tinkerbell. The next one is the hook images URL. Now, what I've found is another interesting thing. This is an optional. If you look at the documentation per se, this is an optional field. Why it is an optional field? Because if you start creating, now what is Hook OS? Like I said, Hook OS is a minimal, booting OS that actually does all the needful to further sequence out the cluster creation or the node preparation. If you don't specify this hook images URL, it is okay. EKS Anywhere has a hosted Hook OS as per the EKS Anywhere versions, and that gets automatically pulled in as the default Hook OS actually if you don't pre-populate this particular URL. But what I have found interestingly in some cases, either you are doing a custom Hook OS or in some cases you want the latest Hook OS. In our case, we had some challenges. I don't know, it could be a caveat, but it did not work with the default provided Hook OS actually, which was a part of the EKS Anywhere distribution. So we had to fetch the latest Hook OS from the GitHub actually. It's a very simple way of actually fetching. There is a link that I will provide in the blog, and you download the tar file, you unzip the tar file or decompress the tar file. You will find two artifacts there, which you can place it under a folder in your web server /hook, and make that publicly accessible. Here in my case, I'm just putting it instead of my web server, internal web server, since I have many other clusters in different labs. I'm just putting it on a S3 bucket there and fetching it from there. And those artifacts. Basically, the init and the RAM disk, basically they are they are made publicly accessible. So again, hook image URL path optional, but as a best practice, it's best to actually download those artifacts, the latest releases, and then put that onto a publicly accessible server or a web server that is reachable from your cluster nodes. The next part is the resource type called as Tinkerbell machine config. Now that machine config is a term used in the Tinkerbell context to describe the type of machine that is being created. So you will see from line 46 to 57, you will see the name of that is POC-POC5-CP, and then what is the hardware selector? The type is control plane. So this machine config will be used to identify the control plane machines. Because we are supplying the URL for a Red Hat, we intended to use this template for a Red Hat based creation. So the OS family is Red Hat. If you are doing a Ubuntu, then this OS family will be Ubuntu. Then the users which will be used or which will be created on those specific nodes, Linux users. So we are using PRD as one of the user and the associated SSH keys for that user. Okay. Now, there are some other variables that you can pass in this machine configuration, but for now, understand that this is the minimal, and this should work flawlessly actually. Okay, so you don't need to kind of bloat out and trying to figure out through the diverse amount of documentation available there. If you're just starting to experiment with bare metal clusters, this is what you need as a minimum. The next Tinkerbell machine config from line 60 onwards, you will see, is named as POC5. I could have named it as POC5-WK. Basically, the type is worker. So this configuration lines are meant to be for the worker nodes. Same thing here, OS family is Red Hat and the users here, right? Okay, so keep this. This is what it takes, that's all. If you go through the actual documentation, I think while it's pretty impressive and exhaustive, it's slightly convoluting to a point that it starts suggesting some custom actions and things like that. Say if you're doing a Red Hat base, then it will say that you need to do advanced configuration for Tinkerbell and all that with custom workflows, and people do get confused to that degree and point where they don't understand what to do with that configuration. I would say if you just are getting started with bare metal clusters, you will not need those advanced Tinkerbell configurations. This is more than enough. Now, we've described 3 resource kinds. One is the Tinkerbell data center config and the 2 machine configurations for the control plane and the worker nodes. Now, where are they referenced in the cluster spec is here. So this, I think you would know from the previous blogs that the cluster, every cluster has a spec, which is the cluster network. The Cilium is the CNI, the CIDR blocks for the pods and the services for the cluster. The control plane configuration count is 1. The endpoint, which will be the API server IP address. Note that this is a separate IP address which has to be reserved or non-conflicting IP address than the Tinkerbell IP. That's different. This is for the Kubernetes API server, which will be running on the control plane. Okay, so this is one IP address. Then the machine group reference for control plane, and this is where you reference the kind Tinkerbell machine config and POC5-CP, which is what we described earlier there. So you reference through this particular attribute the configuration lines here with the control plane configuration. And likewise, the data center ref, the kind is data center config and the name of the data center config, which is POC5 here. The Kubernetes version which will be running on the cluster. So it's going to be 1.28. Note that while in this simplistic configuration, we are just providing a consolidated line item saying Kubernetes version 1.28. That would mean that 1.28 will run on the control plane also and also on the worker nodes. But that's not a limit or that's not a limitation. You can run your control planes on a different Kubernetes version and your worker nodes on a different Kubernetes version. Yeah, I mean, I think they spread out by 2 versions or 1 version. I'm not sure. You can read the documentation. But those are the kind of extra variables that you can pass in your machine configurations when you start populating. You can have that choice, to a point where you can actually do different versions for control plane and different versions for worker nodes and all that. Here we are just doing one version across our control and workers, and this line item is good enough. Management cluster, that EKS Anywhere supports standalone workload clusters or distributed workload clusters managed by a single management cluster, right? Those are two architectures that. So here, because we are doing a standalone workload cluster, the management cluster itself is the workload cluster. So hence the same name as the actual cluster. And lastly, the worker node configuration. The count is 2. We're going to have total of 3 machines, 1 control plane, 2 worker nodes. Ideal recommendations are 3 worker nodes at minimum. This is just a demonstration, so that's okay. So pretty much, if you look at it, this is about it, the cluster configuration. So let's summarize this before we conclude. And in the next set of videos, we will do the actual cluster creation, where we will observe how things progress from the visual that we had shared earlier, actually. So let's summarize what I've shared with you. A visualization of the flow of how this whole sequencing works from Tinkerbell's perspective, and the Pixie boot, and how the cluster node should come up, how the cluster gets created, what is Tinkerbell, what is the role of Tinkerbell here, what is the role of hardware.csv, and the cluster configuration details, actually. So thanks a lot again. In the next video, we will see how to create a cluster with these specific attributes in mind. Thank you.